Very good morning. So all outstation students, have you booked your tickets? Arshini, Ambika? Ambika? Am I audible? Have you booked your tickets?
Yes, ma'am. Yes, ma'am.
Okay. So when are you reaching? When are you reaching VNIT Nagpur? Or April? Why so late? We are planning to start your lectures from 21st. Third and 4th April. Any specific reason why you all are coming so late? It's about. But this was announced quite in advance, isn't it? You knew that you were to report anytime after 21st. Okay, anyway. We'll start our discussion. We have how many? 53 students. An issue. Okay, so we are going to discuss about the mechanism of oil flow, and this is important. This is little complicated, so try to be attentive, focus on whatever we are discussing, and ask questions as and when required. So we are discussing about this journal pairing, which is using a lubricant between a journal and a bearing. What is a journal? Kajal? What do you mean by a journal? Kajal?
Yes, ma'am. Ma'am, it is a machine element which supports moving element.
And what is a bearing then?
Bearing is also machine element.
So journal and bearing is same?
No, ma'am, it's not same, ma'am. The outer part is journal and that outer part is the bearing and inside is, I think, journal.
Yes. So inner part is journal, or journal is an
Yes, ma'am.
extension of the shaft which is rotating.
Yes, ma'am.
Bearing is providing the support, and it is providing a frictionless support with the help of the lubricant inside that. So we were discussing about this L by D ratio, what is short and long bearing, and how this is the length of the bearing and this is the diameter of the journal, and this the part which is shown in gray color, this is the shaft, and this is an extension of the shaft which goes inside the bearing. So this part is what we call as the journal. And there is a continuous oil film. We are going to discuss how this pressure distribution happens to be in this particular shape. and what keeps the journal continuously away from bearing and why there is no contact here. So this is what we are going to discuss, the mechanism of fluid lubrication. Inner ring of bearing, the inner surface you are saying? No, it's not the same. It's not the same. They are different. The inner surface of bearing is still stationary and journal is rotating. But when we talk about the diameter, we talk about the diameter of the journal. So when we talk about this hydrodynamic lubrication or the journal bearing, there is no metal to metal contact. And when we are talking about the friction, if there is no metal to metal contact, what friction we are talking about? We are talking about the friction between the layers of the fluid. There is a thin layer of oil film which is formed, and within the film there is shearing between the layers of the film. Now there are few assumptions. The major ones are the fluid is completely filling the space and there is no metal to metal contact. Flow in the direction perpendicular to the direction of speed, u, is negligible. So we are assuming that the oil is flowing only in one particular direction, only say in x-axis with its velocity u. So as the graph was shown earlier, this one, yeah, this one. So we are assuming this, the lower part is the fixed or the stationary part and this part is moving part. And there is a velocity which oil is flowing only in the x direction with some velocity u. So we are assuming that the flow of oil is only in this direction and there is no flow of oil in the direction perpendicular to this. And the same concept then we'll be using for this bearing. Then the fluid is incompressible. Fluid, when I say it's a lubricant or the oil, and the motion of the fluid is laminar. So there is no turbulence. Even though the journal is rotating at high speed, the flow of oil is still laminar. So these are some of the assumptions. Now, as I said, this part is important. If this is the lower plate is the stationary plate and this is the shoe or the plate which is continuously moving, and then there is a uniform thickness of the oil. The velocity of this oil, it continues to remain u. So this is continuously varying like this. Sorry, here the figure is reverted. This is the shoe and this is the moving surface. So this shoe is fixed. So here the velocity is 0 and here it is having the maximum velocity u. And this is how the velocity increases from its distance from the fixed surface to the moving surface. In case of converging film, which is formed in a journal bearing when a journal is rotating inside the shaft, this becomes the fixed surface and this is the moving surface, and here the thickness of oil is like this and here the thickness of oil is reducing. So here the thickness of oil is say H2 and here the thickness of oil is H1. Now to maintain this area constant, the curve or the distribution of velocity, it happens to be something like this. So at the center where this velocity is same as the velocity for a uniform thickness film, here this velocity gradient is linear. Here the velocity gradient is non-linear on these two sides. So the gradient or the distribution of velocity is such that this area under this solid line, under this solid line and under this solid line, this happens to be the same. Now, as per Newton's law of motion, you know that the shear stress is proportional to the velocity gradient. And if the velocity u is varying with its distance y, with its height y, here the velocity is 0, here the velocity is maximum, then this shear stress is proportional to the velocity gradient. This is del u by del y. And the constant of proportionality is the absolute viscosity of the oil. that is Z. So this du by dy, this remains constant in case of a uniform film thickness. But when this film is converging, so here the height is h2 and here the height is h1, and the film thickness is varying, the velocity gradient is also varying. And so the shape of this velocity diagram, this is the velocity distribution diagram, this no more remains triangular. And so this diagram, this changes in case of converging film. And it changes such that, as we discussed just now, the area remains the same. So whatever is the area under this curve, same is the area under this curve, and same is the area under this curve. And hence here you are seeing the variation in the curve. So this is what happens in the converging film. And when a journal is rotating, we'll see how a converging film is formed. Now let's see how this pressure is distributed here. If I'm taking a small volume of width, this A, this is a small volume. Within this oil film, I'm taking the small volume A somewhere. It's an elementary volume. Along the x-axis, somewhere I have velocity u. And after some height del y, the velocity is little larger, assuming now the moving surface is here and fixed surface is here. So if the velocity here is u, after a distance del y, the velocity is little higher and which is proportional to its height. So this velocity becomes u plus del u by del y into del y. So this is with little increment after this much distance. If we talk about the shearing force, now as I told you, the friction plays a role within the oil film. There is no metal to metal contact. So there is a shearing of oil film, and the shearing always takes place in this fashion, that if the shear force here is acting in minus x direction, the shear force here is acting in the plus x direction. This is what is causing the shearing of the oil film. So here if the shear force is F at this layer, after a height del y, the shear force is F plus del F by del y into del y. Since the velocities are changing and there's a velocity gradient, so the shear force is also increasing. And if we talk about the oil, the pressure on the oil, which is coming into picture because of the load it is carrying. So oil is forming a converging film and it is also carrying the weight of the journal. So there is a component of pressure also. And this pressure is also varying because it's a converging film. So if the pressure here is P, pressure after a distance del x is P plus del P by del x into del x. And if we have to maintain equilibrium of horizontal forces, I want you to draw the figure and label the figure as shown here. I'm writing D here, but read it del. I could not insert del here. So for equilibrium, this is equal to this and this is equal to this, or all these forces and pressure along the positive x direction is same as pressure and force in the negative x direction. And so when we equate this, I get del F by del y into del y when I'm differentiating in x direction. So this into dx is equal to del p by del x dx into dy. And finally, what comes out from the equilibrium equation is the rate of change of force in the y direction, the shear force in the y direction, happens to be same as the rate of change of pressure in the x direction. So the pressure is varying along x direction and the force, the shear force is varying along the y direction. And the rate of change of force in the y direction, that is del F by del y, is same as del P by del x, which is the change of pressure in the x direction. So same thing written in the statement, the change in the shear stress in the y direction is equal to the change in the pressure in the x direction. Please read it, pressure you will get this complete explanation in more details in the book Machine Design by Black and Adams. But we know that the shear force is proportional to the velocity gradient, and so by formula F is equal to Z, which is viscosity, into del U by del Y. So if I differentiate it further with respect to Y, then del F by del Y is Z into the second derivative of the velocity U. And so this is also can be written as del P by del X is equal to Z times second derivative of velocity. So it is this expression of pressure differentiated with respect to X and velocity differentiated second derivative of velocity with respect to Y, which will tell us how the variation in the velocity gradient affects the pressure, and that is the reason we are getting the pressure distribution in the pattern that was discussed yesterday. So we are again going to discuss the same thing today. So I want you to draw this figure, write this expression, and directly come to this equation of pressure distribution. So continuing with this, del P by del X is equal to Z times absolute viscosity times second derivative of velocity U. Let me repeat, U is the velocity of the oil, Z is the viscosity of the oil, P is the pressure, and F is the shear force. Now look again here at the converging film. When this oil is moving between a stationary plate and a plate which is continuously moving, this is how the oil film is forming and the velocity is changing. If we plot a graph between pressure versus this x direction, then this del P by del X, we get the pressure gradient like this, or the graph versus pressure versus the direction x is something like this, where here initially the pressure gradient is positive, it reaches its maximum where it is horizontal, and so the pressure gradient becomes 0, and then there is a negative pressure. So the meaning or the significance of the expression del P by del X is equal to Z times second derivative of speed of the oil or velocity of the oil is indicating, or it is giving this particular curve, a parabolic curve. So for this particular expression, assuming a uniform thickness where the gradient is constant, you can see a straight line. So this gradient is constant, del P by del X, this becomes 0. At the entrance, when the oil is entering the converging film, here we can see the velocity gradient is such that dP by dx or del P by del X, this is positive, and the pressure is continuously increasing. And the pressure will increase in the x direction till velocity gradient is constant. At the constant velocity gradient, this pressure gradient del P by del X, this becomes 0 when it reaches its maximum value. And further, because now this velocity gradient, this is negative, del P by del X will also become negative and the pressure will start dropping. So wherever the thickness of the oil film is minimum, the pressure is also 0. And it is this pressure gradient and this velocity gradient which is supporting the load. So the load is supported only by the fluid which is there in the converging film. So this is very important. This is the converging film which is supporting or carrying the entire load of the journal. And there is the weight of the journal which is responsible for the average pressure coming on the oil. And now this is in general how a converging film is formed and how the pressure is increasing and then it is reducing. And the same concept is used in the formation of oil film in a journal. So this we discussed yesterday. At rest, when the journal is not rotating, it is carrying only its dead weight. the journal, the inner circle is resting on the lowermost point of the bearing. The outer circle is the inner surface of the bearing. The moment it starts rotating at a very low speed, because this area is filled with oil, if it is rotating in anti-clockwise direction, the journal has a tendency to lift up towards the left direction. So the point of contact shifts to B, and the moment it gains its full speed, this entire journal will be lifted up towards right if it is rotating in an anti-clockwise direction. So you can see that a converging film is formed from D to C, which is in the direction of rotation. And from C to D, this is a diverging film. Are you there with me? Hello, are you getting me? So what we are trying to understand here is the point of contact is at A when it is at rest, and then the contact moves to B when it starts rotating, and here there is the angle of the sliding friction, which is given by AOB. As the speed further increases, a film is formed, and this is the hydrodynamic lubrication, where the journal is shifted with its minimum oil film thickness at C. So from D to C, this is the converging film, and this is required for supporting the load. If you see along the length, this is the pressure distribution. If you see across the converging film from the side view, the pressure starts increasing from D where the oil is entering. Somewhere at the middle zone, the pressure is maximum, and the pressure reduces to minimum or zero where the film thickness is minimum, or this is the H minimum. So here the pressure becomes zero. So somebody was asking me yesterday why we are getting this kind of pressure distribution. So this is the logic. So it's only because of the converging film that oil film is formed and it is carrying the load. Since here the pressure is negative, it is continuously drawing oil from wherever it is present, and it is maintaining the fluid film. On the diverging part, since here the pressure is becoming positive, this will not pull oil. So oil is pulled wherever the pressure is negative, and hence this converging film formation is important to carry the journal. Prajwal, you are there? Prajwal, you were asking me yesterday? Yeah. You were asking me why this pressure is minimum at the point of minimum film thickness. So it is the concept of this converging oil film where the pressure at the point of entrance, it is positive, it increases, it reaches to its maximum somewhere here, and then it starts reducing and becoming minimum. So this is the negative pressure. So the point here is it is the converging film which is supporting this load, and it is this converging film at the end of this converging film where the pressure is negative, or dP by dx is negative, because of which the oil is continuously pulled here. So this negative pressure is drawing more and more oil, and this oil film is maintained. So at whatever RPM this journal is rotating, this oil film is continuously formed. So this is about the distribution of pressure. Now if I talk about the radial clearance, what is radial clearance or what is diametral clearance? Sarthak? Vaishnavi? Come on, are you there? Ayush? And so radial clearance is the difference between the radii of journal and bearing. So how the increase in the radial clearance affects the heat generated, how it affects the oil flow rate, how it affects the oil film thickness, and T2 is the temperature of the oil leaving the journal. So with the increase in the radial clearance, This is the heat Q, the heat generated and the heat dissipated. I'm sorry, H is the heat dissipated, Q is the oil flow rate. So more is the radial clearance, more would be the oil flow rate, and continuously more amount of oil is supplied or required since the radial clearance is increasing. So this Q versus radial clearance, this graph is quite obvious. You increase the clearance and the oil flow rate increases. You increase the clearance and the temperature of the oil which leaves the bearing after dissipating heat or absorbing heat. Clearance is more, the temperature of the oil leaving will go on reducing because heat is effectively dissipated. When the clearance is less, more amount of heat is generated. As the clearance increases, the amount of heat generated, this goes down. And if the amount of heat generated goes down, the oil temperature will also go down. So this is heat generated versus clearance. This is the temperature of oil leaving the bearing versus clearance. And this is the thickness of the oil. Oil film thickness or minimum oil film thickness, H minimum. With the increase in the radial clearance, the oil film thickness increases, and beyond a certain limit, if we increase the radial clearance beyond a certain limit, then the thickness of the oil film goes down. So you cannot have any value of radial clearance. So you have to maintain a radial clearance somewhere in this zone so that the oil film thickness is maximum. So this is the interpretation of the graph. Why so? So this H minimum is the minimum oil film thickness, and this allows small oil particles to flow through it. It will avoid the blockage. Now with the oil, there would be some dust particles, some dirt particles, because it's a machine, it is continuously running. So this minimum clearance is required to clear all those debris also. When we are designing a bearing, we'll start solving numericals. We'll see that we have to get maximum possible value of H minimum. That is desirable. Why we want H minimum to be maximum? The value is because we want to avoid this metal contact. There should not be any metal to metal contact. So as is obvious from the graph, you go on increasing the radial clearance, the quality of oil flow, this is increasing, the temperature of the oil, this is decreasing, the amount of heat which is generated, H, this is also decreasing. And practically the value of C is less than ideal because wear increases. So here you see that, say for some value 1.5, H is maximum. But if we keep this as clearance over the time with continuous operation, there would be wear of the outer surface of journal and the inner surface of the bearing, because of which the clearance would increase. With the increase in clearance, the value of H minimum reduces. And so ideally, we will take a value of radial clearance less than this. This is in this gray zone. So with increase in wear, with continuous operation, when the radial clearance increases, the oil film thickness further increases. So practically, we will be taking the value of radial clearance in this zone. So this you have to understand why we are working in this zone. So we have to take into account over the time when it is running for more and more number of cycles, how the wear would take place. Even though there is lot of lubrication, still there would be some wear. So there are debris and there are particles within the oil which will cause abrasive wear between the oil and the bearing surface or the journal surface, which increases the value of clearance. So we'll see what happens when the radial clearance increases by 10% and 15% while we are solving the numericals. Now there are more important terms. One is bearing characteristic number, that is Zn by P. Now this Zn by P is an important term. It's a frictionless number. Z is the dynamic viscosity or the absolute viscosity in poise or in Pascal seconds or in kg per meter second. N is the speed of the journal and P is the bearing pressure, which is load upon the area. Area is always taken as L by D. L is the length of the bearing and D is the diameter of the journal. So the coefficient of friction, this would be a function of this bearing characteristic number Zn by P. This will depend upon the diametral clearance D by C. This will depend upon the L by D ratio, where L is the length of the bearing and D is the diameter of the journal. So this is also known as the bearing number or the bearing characteristic number. And we'll get the relationship between Zn by P, radial clearance, L by D ratio and coefficient of friction in the graphs that are plotted. And they are plotted by two researchers, Raimondi and Boyd, and the same graphs are used for all kind of designs. So as I said, this Zn by P, this is another important parameter, and we'll see how this affects the coefficient of friction. I am expecting you to draw the graphs and the curves and write down whatever explanation we are discussing here. What happens when Zn by P value is reducing, or what happens when this is increasing? This is the curve for coefficient of friction and this is for Zn by P. Below this vertical line, this is the boundary lubrication or the thin film lubrication. Above this vertical line, this is the thick film lubrication or the hydrodynamic lubrication, and this is an unstable zone. This is a stable zone. We have to see why this is stable and why this is unstable. The moment you reach somewhere here, this will tend to move back to this region, and this is a stable region. Why so? What would happen when Zn by P is decreasing? So the moment it moves from P to Q, Zn by P is decreasing, the value of coefficient of friction is initially reducing, and then here the value of coefficient of friction is increasing. So here, if you are moving from Q to R and R to S, the value of mu increases. Now what would happen if Zn by P is reducing? When it is moving from P to Q, the coefficient of friction is reducing, and when it is moving from R to S, the coefficient of friction is increasing. If we are in this thick film zone, the moment coefficient of friction reduces, what happens to heat generated is, if mu reduces, more amount of heat is generated. Temperature of the oil leaving the bearing, that will also increase. When Zn by P is decreasing and the temperature of oil increases, what happens to viscosity? How is viscosity related to temperature of oil? How is viscosity related to temperature of oil? Ameya? Viscosity decreases with the temperature, or it is inversely proportional. And so as the Zn by P decreases, the value of Z is decreasing, the viscosity is decreasing, and the temperature of the oil is increasing. And on this other side, you further decrease the value of Zn by P and the value of coefficient of friction further increases. Now what happens if the load is increasing? The moment the load increases, the pressure on the oil will also increase, because this average pressure is W upon the area. So when the load increases, the value of P increases, and if P increases, this Zn by P decreases. So the moment load is increasing, Zn by P is moving on the negative x-axis, decreasing. Similarly, if N, the speed of the journal, if that is increasing, With the increase in the journal speed, if you are moving in the stable zone, when Zn by P is increasing, the value of mu, the coefficient of friction, is also increasing. With the increase in the speed, more heat is produced because now the journal is rotating at a very high temperature. With increase in the heat, the temperature of the oil increases. With the increase in the oil temperature, the value of Z reduces. Yeah, so when you are moving from P to Q and from Q to S, these are two different sections. So this is for thick film and this is for thin film lubrication. So if you are moving in the thick film with the increase in Zn by P, mu increases, and when Znp is decreasing from P to Q, mu is also decreasing. This initial, you can read this as decreasing. If N is increasing, avoid this, decreasing. Avoid the confusion. So if you are in a stable zone, the moment Zn by P decreases, mu value is decreasing when you are in a stable zone. When the mu value is decreasing within the stable zone, more amount of heat is produced, the temperature of oil is high. With the increase in the oil temperature, the value of Z decreases. And when the value of Z further decreases, the value of mu will increase. The moment the mu increases, you again tend to shift back to this zone. Because then, as the mu increases, the amount of heat dissipation would reduce. So it is continuously moving from this zone to this zone. So from unstable to stable, it has a tendency to come back to the stable zone. With the increase in the load, this value of Znp initially will decrease. With increase in RPM, when N increases, you are moving towards this zone and the value of mu is increasing. As the N increases, more amount of heat is formed, temperature is increasing. Increase in the oil temperature will again bring back this Z. Viscosity decreases and this will again come back in the same zone of PQ. So the moment it tries to shift here, it gets back. So with the increase in N, more heat, more oil temperature, Z goes down and again it comes back to this stable zone if it is trying to cross this zone. So ultimately with increase in N, Zn by P again starts increasing. So the actual value of Zn by P, ideally if we are taking, you will get an ideal value of Zn by P for which this value of mu is minimum. So whatever is the value of Zn by P given in the design data book, the actual value will be always 5 to 10 times of this Zn by P. Because if we take the actual value higher than this, due to running, due to variation in mu, heat, oil, Z value and so on, this tends to come back to this stable region. So if the value of Zn by P is not given in the numerical, we pick up the value from the design data book, we multiply it with 5 times or 8 times or 7.5 times, and that is the value we'll be using for our actual numerical or for actual designing. There is another important number which is Sommerfeld number. I told you there are so many variables here and some of the variables will be given in the problem. Yes, so finally it has a tendency to come back to this region. You increase one parameter, other parameter reduces, it has a tendency to come back here. You try to decrease it and another parameter increase it, it has a tendency to come back to this zone. So we have to always ensure that we are in this stable zone, which is of thick film lubrication. We have to continuously be in a hydrodynamic lubrication. We don't want a thin film lubrication. We don't want a mixed lubrication or a partial lubrication. So that is the concept. And another term which is important is Sommerfeld number S, and we'll get all the graphs and curves which will be Sommerfeld number versus Zn by P, Sommerfeld number versus radial clearance or the diametral clearance, and this Sommerfeld number is another another dimensionless number which is given by Zn by P into R by C whole square. This is radial clearance. And this will depend upon the minimum oil film thickness, amount of heat generated, oil flow rate. And as I told you, we will be referring to the performance charts which were plotted by Raimondi and Boyd. And I want you to solve at least one numerical. We'll start with one numerical within 10 minutes, so you'll get more idea. The formula for heat generated and heat dissipated is given in the design data book. Heat generated would depend upon what is the coefficient of friction, what is the load on the bearing, and what is the velocity at which the journal is running. So this is heat generated. Heat dissipated depends upon the heat dissipation coefficient, the projected area which is L by D, and the temperature of the bearing surface and the temperature of the surrounding air. So all these formulas, all these values are given in the design data book. Let us solve a numerical quickly. Keep your design data book with you. Can I get some space to write? Write down a problem statement. A journal of 60 mm diameter, a journal of 60 mm diameter runs in a bearing at 450 rpm. The bearing is subjected to a normal load of 3.5 kilonewtons. If the minimum oil film thickness required to ensure hydrodynamic lubrication is 0.015 mm. I'm repeating the problem statement. A journal of 60 mm diameter runs in a bearing at 450 rpm. Bearing is subjected to a normal load of 3.5 kilonewton. If the minimum oil film thickness required to ensure hydrodynamic lubrication is 0.015 mm, suggest the suitable oil. If the ambient temperature is 40 degrees and the oil temperature should not exceed 90 degrees. Assume the clearance ratio as 0.001. C by R is 0.001. Also determine the heat loss due to friction. Also determine the heat loss due to friction. And calculate the oil flow required. So let us solve this problem only till selection of oil. This part we'll do it tomorrow. So diameter is given, N is given, H minimum is given, load is given, and the temperature are given. We have to assume some L by D ratio first because we have to refer to graph and all the graphs are given for different L by D curves. What value of L by D you want to assume? Okay, let me make it a standard value. We'll usually by default go with 1.1 or 1.2. Will normally have length little more than its diameter. So let's go with L by D as 1.2. So if D is known, you also know L, and if load is known, you also know what is the average pressure. Give me the value of average pressure. Give me the value of average pressure, please. Rakesh, what was your question? Where are we increasing the load? It's the load on the shaft which increases. What happens with the increase in the load on the shaft? Rakesh, this is what you were asking me. Give me the value of pressure. Yeah, so how can we increase the load? It increases with more and more installations on the shaft. It's carrying a pulley, it's carrying a sprocket, it's carrying a gear. So the moment you pick up or you design something which is heavier, the load increases. Okay, so this is 0.81 MPa. Now we have to find out the oil, which means we have to find out the viscosity. And we'll get the curve for Sommerfeld number, which is Zn by P into R by C whole square. R by C is known, N is known, P is known. If we get the Sommerfeld number for this L by D ratio, we can get the value of Z. We also have H minimum by C. This is known to us because C by R is known to us. R is known. So H minimum by C is also known. So if C by R is known, give me the value of C, give me the value of H minimum by C, and then we refer the graph for Sommerfeld number versus H minimum by C. Give me C first. Diameter is 60, radius is 30 mm. So what is the value of C? .03. So what is H minimum by C? H minimum by C 0.5. Refer to the graph on page 136. H minimum by C versus Sommerfeld number. So for H minimum by C as 0.5, L by D as 1.2, somewhere between 1 and 2, give me what is the value of Sommerfeld number. Refer the graph figure 13.5, page number 136. Give me S. H minimum by C is 0.5. L by D ratio is 1.2, so little above 1. For the Sommerfeld number, the first vertical line is 1 into 10 raised to minus 2, next is 2, 10 raised to minus 2, 6, 8, and then it is 10 raised to minus 1, 2, 10 raised to minus 1 likewise. You have to read it likewise. What is the value of Sommerfeld number? 1.5, 10 raised to minus 1. Do you agree with me? Whatever is the value, the next one is 2, which is 2 into 10 raised to minus 1. Next vertical line is 4, 10 raised to minus 1. So if you are getting a value between 0 and 1 and 2, it is somewhere 1.5, 10 raised to minus 1. Kaustubh, give me the value of Sommerfield number. Prajwal, Deepika. Around 1.5 or 1.6, 10 raised to minus 1, which is 0.15. So if you know S, you know N, P, R, C, everything is known. Give me the value of Z. This is Zn by P, R by C. Give me the value of Z. You'll get the value of Z in millipascal seconds. This is unitless, dimensionless. Give me Z quickly. Z, are you getting 0.00027? And 0.027. Any other answer? Yeah, it is 0.0162. This you are getting in Pascal second. This is in Pascal second, or yeah, I'll tell you again. This is 16.2 millipascal second. So what is given in the graph is in millipascal second. From this value of Z and from the oil temperature 90 degrees, we have to select the oil. We are going back to how to read the axis for S. Along the x-axis, the first vertical line along the x-axis for Sommerfield number, that is indicating 1 into 10 raised to minus 2. Second vertical line is 2, 10 raised to minus 2. Third is 4, 10 raised to minus 2. Then 6, 8. And then next line is 10 into 10 raised to minus 2, which happens to be 10 raised to minus 1. Next is 2, 10 raised to minus 1. Then 4, 10 raised to minus 1, likewise. So for L by D 1.2 and for H minimum by C 0.5, you are somewhere between 1 10 raised to minus 1 and 2 10 raised to minus 1. And so your value is around 1.5 to 1.6 into 10 raised to minus 1. Is that clear, Vaishnavi? Okay. So the value of Z that you got was in Pascal second, which is 0.0162, or it is 16.2 millipascal second. And for absolute value of 16.2 millipascal second, refer the figure 13.2. It's given the oil temperature not to exceed 90 degrees. So around 90 degrees for 16.2 absolute viscosity. Give me what is the oil Which grade of SAE? Figure 13.2. SAE 40, right? So here on the y-axis, the absolute viscosity, this is given in millipascal second. And you are getting SAE 40. Which can withstand a maximum of 90 degrees with absolute viscosity 16.2 MPa. So we'll solve the remaining part of the problem in the next class, and we'll have more number of numericals. But once you understand the concept of hydrodynamic lubrication, all we have to do here is only play with these variables. So as I said, some parameters would be given, other parameters we'd get from the graph, and the numericals would be much simpler for bearing as compared to whatever we have done till now, gears and belts and so on. Ask me if you have doubts for whatever we discussed till now, else we'll stop here. I so much wanted to teach this topic in physical mode. It's so difficult to teach you without seeing your faces. So it would be better if you come to campus as early as possible, and if we can start in the physical mode. It's easy to interact. So what we have done here is we have assumed an L/D ratio. We have calculated the pressure from the load and the cross-section area. And from the C/R ratio which is given, we have calculated the clearance. And since we are using the graph for Sommerfeld number versus H minimum by C, we have calculated what is H minimum by C. We are referred to the graph on this figure. We got the value of Sommerfeld number. And from S, you get the value of Z. And from Z and temperature, we select the oil. If you have no doubts, you are free to leave. Thank you.
Ma'am,
Yes?
ma'am, are we having class on Friday?
Friday, we don't have a regular class on Friday, right? Thursday we have lectures, no? In our timetable, we have lecture on Thursday and then on Saturday. Why this
Yes,
question?
ma'am.
Yeah. Thank you.